Hey guys, how you doing? I hope you're doing well. So, welcome back. This is our second official lecture. So we had our intro, then we had our one uh, matter units of measure. Now we're going to be talking about atoms and atomic structure. This is our intro to that particular lecture. So I'm going to go through a couple of things in these intros from here on out. One, I'm going to tell you the topics that we're going to talk about. Two, I'm going to go over the quiz for the day. This is the first time you're going to have a quiz for today. So lecture 2 is the first quiz. All right. So understand that I will be going through each of these. Again, these quizzes are just informational for me. They are either pass fail, you either take them or you don't. It's a way for me to keep track of who's attending when, that kind of stuff. If you miss a quiz, sorry, I will not open it up for you again. That's just not the way I'm going to do it. Since they're pass fail, I'm not doing it. I have never had a situation where a student missed a quiz and said to me, "Oh, well, that could have made a difference," where it actually did. Okay. But if you think that you want me to look at it, if you've missed quizzes and at the end of the term you want me to look and see if it would make a difference if I gave you those points back, then we can do that. It's never happened, but that's okay. I'm still offering it up. Okay. Now, what are we going to be talking about? Well, here are our topics for this particular set. We have atomic theory of matter, the atomic mass unit, which is an AMU. We'll talk about mass number, atomic number, and the atomic symbol. We'll talk about isotopes, what an atomic mass is, atoms, ions, and molecules. We'll talk about the periodic table and some periodic trends. So those are the things that we're going to be covering today. We'll take some breaks in there. We'll try and get some sections in this. I'm going to do this one a little bit differently. So it's going to go, with one video that has chapters in it, I hope. So hopefully that will work, but that's how we're going to manage this particular one because it's less work on my end and hopefully still the same kind of thing for you. Now, what are we doing? The first thing is this is what's in your quiz. Now, it's either exactly the same or very close to it. It may not be exactly the same, but it's a very similar idea. Okay. And again, I'm going to say to you at this point that there may not be 100% match between the quizzes that are there and the material that we're talking about at this point. That's kind of the way this goes. I'm updating things as we go, and so it may or may not match. I can't guarantee it, but this should be fine. It says to calculate the mass in grams of 2 cubic inches of gold. So I have 2 in, oh, I didn't want that one. I wanted this one. 2 inches cubed. Cubic inches means cubed. I want you to take a stab at this, have taken a stab at this first. So pause here and see if you can get to a mass in grams on your own. And then come back and we'll talk about it. Okay. So starting with that 2 inches cubed. 2 inches cubed. I know that I want to get to a mass in grams. So I also know that the density of gold is in grams per centimeter cubed. So if I can get to centimeters cubed, I should be able to get rid of the centimeter part and leave me with grams. Well, that's awesome. But I'm in inches at the moment. So I also know that 1 inch is 2.54 centimeters. Now remember, because this is inches cubed, I need to cube technically this whole thing. It's both the top and the bottom. What happens when I do that is, and I'm just going to write this again so that we can see what we're talking about, is I end up with 1 inch times 1 inch times 1 inch, which is equal to 1 inch cubed. Okay, so that's what that's looking like on the bottom. Now on the top part, we'd be talking about 2.54 centimeters times 2.54 centimeters times 2.54 centimeters, which of course I can put in on my calculator as 2.54 cubed. Okay, so that's the way that works. We need to make sure that we've done that. Now, once that's done, that gives me an inch cubed, canceling with an inch cubed, and it leaves me with centimeters cubed on the top. Okay, I have centimeters cubed on the top. I want grams, and I have grams per centimeter cubed. So 19.3 grams is 1 centimeter cubed. So that centimeter cube will cancel and leave me with an answer in grams. Well, awesome. That's amazing. And that means that that's the calculation that I need to have set up. All right. Now, again, as we've talked about before, and I'll show you on the calculator one more time, I won't do this forever, but this is something that I'm going to show at this point. I'm going to do this. All right. So 2 inches times 2.54. Again, I'm going to cube that. And then I need to go down times 19.3. And when I said I need to go down, that means I need to get out of the exponent. Because if I don't, then I'm going to end up with 3 times 19.3 as my exponent, and that's not right. Okay, the math on that is definitely different. And if I do that, I end up with this lovely number, 632.54067004. Now, looking at the numbers that I've been given, that 2.54 is not relevant. I mean, it is, but I don't use it to talk about sig figs. So 2.54 is infinitely known. Density is also a conversion factor that I've been given. It is infinitely known. So the only number I have that has number of sig figs that I can work with is the 2. Here it's 1 sig fig. So my answer should be 1 sig fig. So I either report that as 600 or 6 times 10 to the 2 grams. Okay, that's the way I'm going to do that. All right, and it's 1 sig fig because a 2 is 1 sig fig. That's it. So questions, comments, problems on our practice. So I'll leave this here for a little bit. You guys can stop it and look at it as you need to. Since we're now at a question point, we would now take a break and go to our next chapter. So hopefully I'll remember that this is where the chapter goes, is here. Now the next thing we're going to talk about is the atomic theory of matter. Elements are composed of extremely small particles that we call atoms. You've probably heard this before. All atoms of a given element are identical. They have the same size, the same mass, the same chemical properties. Atoms of one element are different than another element. That's why they're different elements. Compounds are composed of atoms of more than one element. For a given compound, the same types of atoms are present in the same number. Now, I alluded to this the last time. So we talked about the difference between H2O, which has 2 hydrogens and 1 oxygen, and H2O2, which has 2 hydrogens and 2 oxygens. Okay, those are completely different things with completely different characteristics. All right. Now they have a lot of some similarities. It depends on what we're talking about, whether they're similar or different. Okay. So we need to understand that this fixed ratio here is different than this fixed ratio, and we'll be able to calculate that once we get there. Chemical reactions rearrange atoms. So I could have a chemical reaction where this H2O gets broken down, and it gets broken down into 2 different things. This is what happens to your hydrogen peroxide, which is H2O2, when it sits around. It goes through a reaction, and it becomes H2O and O2. Those are the 2 products that it has. Now, for anybody who knows how to balance, I haven't balanced this. Okay, those are the 2 things that it becomes. That is something that we would do in a chemical reaction. It's a rearrangement of those atoms. It does not create them, it does not destroy them, and that's why I'm talking about it not being balanced. We'll get to that. I haven't gotten there yet. That's actually later. It's right before the first test. Another thing we need to talk about is that the atomic theory of matter talks about what we call an atomic mass unit, an AMU. It's called an atomic mass unit. So that is a way that we can talk about the mass of a particular atom, thing, and we call it an AMU. Now, what the hell is an AMU? What does it mean? How is it defined? We'll get to that in just a minute. But I wanted to talk more about the structure of the atom before we go on. Now, if we know about anything about our elements, we know that there are a couple of things that happen within that atom. I have a couple of different types of particles. I have a neutron which is neutral. I have a proton, which is positive, and I have an electron, which is negative. All right. My electrons were discovered by Thomson. They're negatively charged. They're very, very tiny, and they're distributed throughout the atom. They're all around the exterior. They're not in the middle. Okay, but they're around the exterior, and they're around the exterior in ways that we can talk about. They don't really look like this picture. This is what we call the Bohr model of an atom. And you may be asked to draw a Bohr model, and that is just something where we talk about the circles of electrons around the nucleus, which contains the proton and the neutron. Now, when we talk about our protons and our neutrons, protons were discovered by a guy named Rutherford. They have positive charges. There are the same number of protons as electrons in a neutral atom. So our atoms are always neutral. We'll talk about this again. Same number of P plus as E minus, because that's one of the ways that we talk about them. We'll get to that again. Those protons are large. They're very large comparative to an electron. And we say that they're one atomic mass unit. Okay? They're centrally located, so they're in the middle, and it contains approximately half the mass of the atom. Okay, so it's roughly half. Okay? I also have neutrons. Neutrons are the mass of each one is an atomic mass unit. Mass of all neutrons is just over half the mass of the atom. It depends on how big it is, whether it's half or more. The heavier you get, the more of them you need. Okay. These particles have no charge, just mass, no charge. So you'll see their symbol is here. There is no charge there. My protons, since they're positive, have a plus in them. My electrons, since they're negative, have a negative in them. These are bigger because they're each one atomic mass unit. My electron is very, very small comparative to that. You need to be able to draw this. You should know that in a neutral atom, the same number of protons is equal to the number of electrons. Therefore, my charge equals 0. So P plus equals E minus. Charge equals 0. Okay, so in a neutral atom. All right. Do you need to know who discovered these? Not really, no. But I feel weird if I don't tell you these things. So that's that. So you should be able to draw one of these Bohr models. Now I happen to have drawn you a carbon atom. He's here. He has 6 protons. He also has 6 electrons. You can count 1, 2, 3, 4, 5, 6. And there happen to be 6 neutrons in here as well. Okay, so that is one of the carbon atoms that we have. Cool. That's the structure of my atom. And that's what we're talking about when we talk about atomic structure. Now, when we talk about those chemical changes that we talked about before, and I said that you couldn't change that you'd have to do a chemical change to do things differently, that means that we'd have to break the bonds. Okay, if we're breaking the bonds between them, that changes the arrangement between them. That's a chemical reaction. All right, if we're actually breaking down the structure of the atom, that is a different type of chemistry, and that is nuclear chemistry. So if we can't, in a normal chemical reaction, change the number of electrons, protons, yada, yada, yada. We don't really deal with that. And we can take electrons off and we can put electrons on. That is possible. But we're not talking about changing the number of protons and neutrons ever, unless we're talking about nuclear chemistry, which we will get to when we talk about balancing reactions. Okay, so things to come. Now, again, our atomic particles, I want to reiterate to you that a proton has a positive charge. Its mass in atomic mass units is approximately 1. It's 1.0073. A neutron has no charge, it's neutral, and our mass is 1.0087, so it's slightly larger than a proton. Our electron, which is negative, is teeny tiny comparative to that, okay? And what you're looking at, and actually I should have these symbols in here. This is a P plus, and this is listed as an N0. Now that thing in subscript is actually the charge on this thing. And you may see it in Alex as P plus 1 or E minus 1. There may be a 1 there, there may not. You don't have to put it if it's a 1, so, it's all right. But those are the symbols that we use, and I should have put them on the actual slides. So I need to fix the slide because I meant to do that when I made these changes. Sorry. But what you can see from that electron is that they're teeny tiny, times 10 to the minus 4th. And that's why we say that they're little bitty comparative to the other things, and that they don't give us much mass in terms of what we're talking about. And we're going to start talking about atomic orbitals and the ways that they look. There are different types of orbitals. An orbital is the space that an electron can live in. And I said before that they don't really look like this. They're not all circles around that central bit. My electrons don't exist in these lovely circles that we've drawn here. What they exist in are things that look like this. Some of them are circles. Some of them are dumbbells. Some of them are kind of like four-leaf clovers. And some of them are so complicated I don't even want to think about it. All right. Those are the way those things look. And what those represent is where you have a statistically higher probability of finding the electron density in a particular atom if you could look at it at that size. You don't need to know what those structures look like, okay? It's important that you know that they're different, and we'll get to that. That is something we'll come back to. But they don't have that circular structure around them, and this is what we actually are looking for, okay? So that's what they actually look like. We don't necessarily talk about that much in this particular class. This has to do with something called molecular orbital theory, and that is a theory we don't talk about in general chemistry here. We talk about it in organic chemistry. So if you're going to take the 200 series, that's when you'll talk about that. All right. I just said this. So why are we doing this again? I have my proton. Again, I can say he's a P plus or P plus 1, any of those. My neutron is an N0. He has no charge. My electron is E minus. He may be a minus 1. 1 minus works as well. Charge is given. Positive, none, negative. Symbol, plus, N, E minus. Okay, that's one way that we can talk about them. This is another way that we can talk about them. Different things use different things. So, atomic mass unit, approximately 1, teeny, teeny, tiny. All of these things that we've been talking about actually have real meaning to us as we start to study chemistry. Okay, the number of protons, those positive charges in the middle of that atom, determine what element we're looking at. So if I know the number of protons, I know the element that I'm talking about. If I'm talking about an element that has 7 protons, then I know that that is nitrogen because he's number 7 on the periodic table. So the number of protons, this, is equal to the atomic number. Okay, so the atomic number is the number of protons. Right? Other things that we see when we talk about this. Some periodic tables have the physical state. This particular one does, and it tells you that in its native state, nitrogen is a gas. Okay? The periodic table you get on your test won't tell you that. It's not really that important that you know it. It is something that we can learn from the trends that we'll talk about a little bit later. This particular table tells you that this N means nitrogen. So N is its symbol. Notice the atomic symbol is N. The atomic name is nitrogen. So name and symbol go together, all connected to the number of protons. Those are all related to each other. I also know that there are 7 electrons that exist in this particular thing. If it's neutral, this number of electrons should be equal to the number of protons. So one more time, number of protons should equal the number of electrons if it's neutral. All right. And so that tells me that there should be 7 electrons that are present in this, 7 total. You'll see that this thing has this wonderful little thing down here, which may or may not make any sense to you right now. If you have taken chemistry before, it probably looks familiar. If you haven't, we'll talk about it. This is called an electron configuration, and it tells you how many valence electrons this thing has. So this is in the outermost shell. So if we're looking at one of these models, it'd be the stuff that's on the very edge that we can actually do some stuff with. Okay? Anything that's in the interior portion, we can't really get to do anything with. So these electrons that are on the outside, it's more important that we can talk about them and what they look like, because that's where the chemistry is going to happen. The other thing you're going to see on a periodic table is an atomic mass. That is this number right here. Now, an atomic mass is not the same as the mass of an isotope. The hell does that mean? Well, we talked about the number of protons equals the atomic number. It's the number on the periodic table. The number of electrons should equal the number of protons in a neutral atom. So if you have no charge, the number of protons equals the number of electrons. My number of neutrons, how many there are, determines which isotope I am dealing with. I'll talk more about isotopes in just a second, but that number of neutrons tells me what that isotope is, all right? So remember that isotopes have to do with the number of neutrons that I have, because they don't have to be the same, right? It's generally equal to or greater than the number of protons. So that's a lot of information. Not all periodic tables have them. And when we talk about an atomic mass unit, its definition is the mass exactly equal to 1/12 the mass of one carbon-12 atom. Well, that's great if I know what a carbon-12 atom is. Well, a carbon-12 atom is this thing right here. And what this means is that I have 12, 6, C. Now, C is the atomic symbol. 6, this number down here, is the atomic number. And then this 12 that's up here is my isotopic mass. Notice I did not say atomic mass, I said isotopic mass. What that comes from is if I know what that isotopic mass is, it tells me that the isotopic mass is equal to the number of protons plus the number of neutrons. Okay, so if I have an isotopic mass at 12, and I know that the number of protons is 6, then the number of neutrons is also 6, because the only way I can get to 12 from 6 is to add 6. That means I have 6 neutrons. That's not always the case. Okay, sometimes it is, sometimes it isn't. So if I know the isotopic mass, I know exactly how many neutrons I have. These numbers on the periodic table, though, are never these nice, pretty, even numbers. They're not like that. And so the question becomes, well, what does that actually mean? Why is it different? And that's why we need to talk about this. Isotopes are different things that have different number of neutrons. Okay, so 12,6C is one isotope of carbon. The atomic mass unit is based on 1/12 the atom of this thing. Okay. But there are other isotopes of carbon. So again, we're talking about that mass number at the top, atomic number at the bottom, and the atomic symbol. The atomic number determines the atomic symbol. The mass number is the sum of the protons and the neutrons. And again, since they're both approximately 1, we'll have whole numbers when we deal with this. Now, if we're talking about carbon, the number of protons is always 6. If the number of protons change, it's not carbon anymore. All right, so they're all number of 6. Since it's a neutral carbon that we're talking about, the number of electrons is also 6. Okay, so protons equals electrons equals 6 for carbon. Now, if my mass number up here is 11, and my number of protons is 6, I take 11 minus 6, that gives me 5 neutrons. 11 minus 6. The 6 that's here comes from the mass number of 12 minus the 6 for the protons. That gives me 6. The mass number here being 13 minus the number of protons. That gives me number of neutrons, which is 7. And then here, my 8, that comes from the mass number of 14 minus the atomic number, the number of protons, which is 6. Okay, these are all neutral ions. Okay, but that's how I figure out how many neutrons are in this thing. So for an isotope, I can figure out exactly how many neutrons I have. Cool. That's awesome. Showing it again. Isotopic mass. 6 plus 5 is 11. 6 plus 6 is 12. So that gives me that 12 up there. The isotopic mass given in the far right column is the number on the top of the symbol of the element. So it's that mass number. In the case of an isotope, the mass number is equal to the isotopic mass. It's just the sum of those two things. That's it. Okay. Atomic masses are not the same as isotopic masses. They are not the same things. The atomic mass is the sum of protons and neutrons as it exists in nature. All right. And I told you that there were 4 isotopes of carbon. Those 4 isotopes don't occur in equal numbers. All right. So sometimes we have carbon 6, carbon 12, sometimes we have carbon 13, sometimes we have carbon 14, sometimes we have carbon 11. So we have a mass that exists in nature. That's the mass of each isotope times the fraction of the total population that's from that isotope, right? That happens. We can do that math to figure this out. The atomic mass, what you see on a periodic table, represents that nature system that you're looking at. How much of it, of each of those isotopes that exist, appears in nature. Okay? So those masses are never nice, even numbers. If I'm asking for an isotopic mass, I may not say isotopic mass. I may just say, what's the mass of this isotope? I might say, what's the mass of this thing, where you have a mass number and number of protons, or, sorry, atomic number and a symbol, and our generic symbol that we need is X. So, you know, I may be asking you for what is that mass number based on the number of protons and neutrons that you have. Okay? Make sure you read the question to understand which one that we're talking about. All right. And the mass of a mole is given in grams, and we'll talk about that in moles in the next lecture. Okay. So isotopic mass, not the same as an atomic mass. Atomic masses are averages of everything that exists in nature. I will not ask you to calculate those, but you need to understand that they are different. So again, here, I can go through how we would calculate an atomic mass. Now, I'm telling you how you would calculate it, only so that you can understand that they're different. All right? I do not expect you to do this, but this is how we get from what that nice, whole number is to the numbers that we see on the table. Okay? And it's based on how they exist in nature. Right? Are there any questions on any of the things that we've talked about? So the atoms that we have, the isotopes that we've talked about, atomic masses versus isotopic masses. That's what we've been talking about. So hopefully that's going pretty well for you. All right, I'm going to take a break for just a second. I'll be right back. All right. So having talked about that, we talked about an atom. We talked about the isotopes. Now, let's talk about the next piece that we need to be able to talk about. Everything we've talked about so far are atoms. Atoms, again, are neutral. They have the same number of protons as they have electrons. They're the smallest unit of a discernible material we cannot break down without chemical changes. Now, some things exist as dimers. Oxygen, when it's by itself, is always O2. It's a diatomic gas. There are 7 of these that we will eventually ask you to know. You don't need to know them right this second. So some of the gases always exist as dimers. Otherwise, we're talking about an individual carbon atom or an individual nitrogen atom, okay? We can break them into individual atoms, right? Only the dimers are things that we need to keep track of. That's the elemental form of those things. Now, we can make something called an ion. And what that is when an atom loses or gains electrons. So depending on where I am and certain circumstances that we'll get into, that atom can lose electrons or it can gain electrons, and therefore it's going to have a charge because my protons are no longer equal to my electrons. So remember that when protons equals the number of electrons, that was neutral. And so if I lose electrons, my number of protons is greater than my number of electrons. And so if that's happened, then that's a positive charge. I lost negative charges. If the number of protons is less than the number of electrons, i.e. I've added electrons to this thing, then that's a negative charge because those electrons are negative, okay? So it's a little bit backwards. I understand that. So we can gain and lose electrons depending on where we are and what we're doing, and we have to show that charge. Because if I don't show the charge, then I think that this is neutral. So we always put the charge up in the upper right. So mass number goes in the upper left, atomic number goes in the bottom left, and my charge goes in the upper right. I can leave it as negative if it's 1, it's an implied 1. If it's a 2 or 3, we either have to put it as 2 minus or minus 2. I prefer to put the number first because it emphasizes the number when it's first. So be careful with that. Just make sure they look like negatives or positives. Okay, but we need to have the charge up here. So again, we're talking mass number, symbol, atomic number, and charge. Okay, so that's where we've gotten so far. Sweet. If we can talk about the fact that we've lost or gained or whatever, we need to talk about how many protons do I have? How many electrons do I have? That's a fairly easy thing for me to talk about. Now, at this point, I want you to pause. I want you to look at the information that you've been given. And I want you to tell me how many protons do you have in that species and how many electrons do you have in that species. I'm going to make a table. Table here. So number of protons, number of electrons is what I'm going to be looking for. So I'm going to take that symbol that I have and I want to find out how many protons and how many electrons. So I'm going to draw this while you guys are thinking about that. I want you to do that. Once I'm done drawing this table, I'm going to ask you to pause and do this for yourself before I show you how to do it. And hopefully I left myself enough room to do that. All right, you ready to talk about this? Now, in order to find the number of protons, I have to look at the atomic symbol. Now remember, if I look at the atomic symbol, that should tell me where it is on the periodic table, and therefore I should be able to figure out how many protons it has. So I need to look at a periodic table. I am going to pull up for you, I'm going to pull up the exam handouts, and we'll talk about the one that's on there. So this is the periodic table that's on the exam handouts. I'm going to put this over here. I'm going to see if I can zoom out a little bit. It's not quite the right size, but okay, we'll work with this. Well, I might be able to do That's better. Okay, so now I can see my periodic table. I'm looking for Cl, chlorine. Now, I happen to know that Cl is right over here. Now, if you can find them on the periodic table, that is really, really good. Sometimes it's really hard for me to find them, okay? And so I need a little better way to find that, and that's where this comes in. Okay, now this is arranged in atomic number order, but sometimes it's easier for me to look through this and say, oh, there's Cl. He's the chlorine, he's right there, and that says he's number 17. Scrolled over, but he's 17. Okay. So now that I know he's number 17, then I can go find him. Wait, whoa, 17's right there. So that's where he is. It's going to be important that we know where he is eventually, but right now all I need to know is what his atomic number is. If his atomic number is 17, that means he has 17 protons. Atomic number equals number of protons. Now, I'm going to do all the protons first, because for me that's easier. I know what that looks like because it's on the periodic table. All I got to do is find it. So I know that my hydrogen is up here, this corner right here. His atomic number is 1. Phosphorus is over here. And that's very hard for me to read. His atomic number is 15. Oxygen is up here. His atomic number is 8. Calcium is over here. And calcium has an atomic number that is 20. The next one that I'm looking at is magnesium, Mg, which is right above that. Okay, Mg. And of course, he's right above that. His atomic number that's listed is 12. Fe. Now, I don't necessarily know what Fe is, but I can find him in my table if I'm lucky. Yep, he's right there. I can't really see that. It's hard for me to read. So, I'm getting old, so I gotta come in here and say, okay, where. And of course, when I'm on the computer, I can cheat and search. You go. Love it when I lose things. Iron is 26. Oh, there he is, Fe, which is iron. He's 26. Thank God I found it. Again, I couldn't read my periodic table. So, all right. N. He's right here. Now, I know if oxygen's 8, that means that nitrogen is 7. Because they go in order in the table. I have noticed that the numbers, this is 1, this is 2, this is 3, 4, this is 5, 6, 7, 8, all the way up to 8. I may not understand why they're the way they are, but the things that are presented, as long as I go across the rows, that's the order that they appear in until we get towards the bottom. And then carbon. We talked about carbon before. His atomic number was 6. So those are my atomic numbers. Now, for anything that's neutral, so there's no charge indicated on it, the number of electrons is the same. So the ones I have that are neutral, this is neutral, this is neutral, and this is neutral. So those 3, protons equals electrons. So this should be 15, this should be 12, and this should be 6. Okay? Awesome. Now, for me, it's easier to think about the negatives first because I'm adding a negative charge. So I've added an additional electron. So chlorine, which should have 17 electrons, is now negative because I added 1 more. That means he has 18 because he is negatively charged. This is also a negative charge. This is also a negative charge. Okay, now I'm going to go straight down. I'm just going to list these as the charges that they are, negative, positive, and I'll talk about why once I've done all of what's when we're done with this. So the next one is hydrogen. He's listed as H+. So if he's positive, that means he lost an electron. He lost a negative thing, so he became positive. And he had one proton. He's now positive. That means he has lost that one electron, and he has none. And this should be a superscript. Making notes so I can try and fix things. Okay, well that's cool. Now the next one that I have to deal with, because I already did this phosphorus, I have my O2 minus. O2 minus had 8 protons. Now I've added 2 electrons. That's why he's negative. I added 2 negatives to him. So I added 2 electrons. I'm going to go from 8 to 10. Okay. Calcium is listed as a 2+. So he had 20 electrons to equal the number of protons. So he had 20, and he's lost 2 to make him positive. That means he has 18 left. So 20 minus 2, 18. Awesome. I already did the magnesium, 12 and 12, because he's a neutral. Fe3+ has also lost electrons. He started with 26 electrons and has lost 3. 26 minus 3 is 23. N3 minus, he started with 7 electrons, which is equal to the 7 protons. But now I've added 3 more. That's how I got that 3 negative charge. And that means that I now have 10. Okay? So remember, a couple of things that I want you to remember from this. I use the atomic symbol to find the atomic number. The atomic number is the number of protons. I then look to see if it's positive or negative. If it's positive, I take away electrons. If it's negative, I add them. If it's neutral, I know exactly how many there are. Okay, so that's why I did the neutrals first, because it's even and I don't have to do any math. Not overly great with math. So if it's negative, then I add. If it's a positive charge, I subtract. In my head, I have managed to associate those in such a way that it doesn't confuse me anymore. But I know that when I started, it was incredibly confusing. I didn't like it. I wanted it to change. I wanted it to not be the way that it's supposed to be. And physics and chemistry have been arguing forever about whether or not these charges are right, you know. So I'm not even going to get into that part, but this is the way that it is. Electrons are negative. So if I add them, I become a negative charge. Okay, it's backwards. Just remember, you're adding a negative. And you can do the math, you know, with your calculator. If I say, okay, I have 17 and I add -1, that tells me that I had 17 and I add another electron to it. So I add another 1 to it. That's an 18. So that's what I got. All right. So that is how we determine how many protons and how many electrons. That's sweet. Awesome. I can do that. It's going to take some practice. I know that it's going to take some practice, but you need to make sure that you're getting good at that, because these charges matter. The number of electrons will matter. All of these things will come back to visit us as we move forward. So this is important. Okay. Questions, comments, problems at this point? Okay. Now, I have presented to you atoms. I have presented isotopes, which are atoms that have different numbers of neutrons and therefore different isotopic masses. I've talked about how the isotopic masses lead to the atomic masses, which are not the same as the isotopic masses. Okay, it's a weighted average. We've also talked about how we get ions, which are charged particles. Cool. The next thing we're going to do before we start talking a lot about the periodic table is start talking about the structure of that table. Now, there are some things that happen with our periodic table the way that we put it here. Notice that this doesn't look the same as what you're looking at right here. It doesn't. And that's because these two things right here actually belong right there. But that makes it very difficult to fit on a single piece of paper. So we normally sort of excerpt them out. We leave the LA and the AC, right? And those are the ones that come, the gap right here is where the LA and the AC go. We then come to the end of the LU and the LF, and then we come back to the HF, right? That's here. So then we come back to the HF that's here in this block right here. This is the block that's right here. And then we go back into this block that's over here. Okay, I'm going to tell you, and I'm just going to mention it right now. I'm not going to talk about why yet, but these are blocks. I talk about them as blocks. I talk about this as the F block. This is the S block. This is the F block. This is the D block. And this is the P block. What that means is that when we talk about it over here, and we've got this pulled out, these are S, this is D, this is P, and this down here is F. Okay, we'll talk about that a lot more. But if I accidentally slip and say that, that's what I'm talking about. So that's how it should appear. And that should, the numbering there makes a lot more sense than what we're actually seeing over here on this little page. But that's just done so that we can get it on one piece of paper and deal with it. All right. There are views of these kinds of things on the internet that you can go out and look for. And what I did was I Googled periodic table with F block in the right place, I think. And then I found images that would show me what that would look like if it was an excerpt. Okay. That was helpful for me. When I first saw that, it gave me a better understanding of what it was that I was looking at in the shortened version. So that's why I present it. This also can talk about this view that you have, which you will not get on a test. We'll show you where your alkali metals are, your alkaline earth metals, your transition metals, your, I think that's, well, I can't actually read that. So, but all of the different types of groups that are in here, all of these things, these are metalloids, these are non-metals, these are noble gases. Yeah. So those are all the different things that we talk about. And so you can talk about those. We do sometimes refer to them as the types of materials that they tend to be, and that's what this is referring to. Okay. Now, when we talk about our periodic table of the elements, and this is a slightly better view so that you can read those things a little bit more, this is the view that we typically look at. Again, this is not the view that I'm going to give you on your periodic table for the test, because this gives you more information than what I think you should be presented with when you're taking the test. So we have an atomic number, a symbol, a name. There's a bunch of other. There's the atomic mass is down here. We've got some information over the top. It talks about 1A. You'll see this is 2, Roman numeral 2A, and then 2A. This is all the different nomenclature that we've used for these things over the years. Current practice is to label this 1 through 18. So 1 through 18. But your textbook, even though it presents it that way, Alex still talks about like 2A and 5A and a couple of things like that. So you need to understand that that's where those come from. Is this other the old numbering systems. Okay, these are not on your periodic table that you get on the test. They're just not. All right. So there's some names: lanthanide series, actinide series. I'm not going to ask you some of these. These are these different things that we were talking about here. Okay, so they call them metalloids, semi-metals. That's what this group is. Okay, and again, this came from this particular place, and they have 8 billion different types of views on that particular page that you can look at. And that's where I got most of these from. Cool. Information on that table. We've talked about this a little bit. I gave you this in one of the things that was there. I can see an atomic symbol. I can see an atomic number. I can see an atomic mass. I can see groups. What do I mean by groups? Groups are the columns. So groups are columns. Okay. Don't get confused. Groups are columns. Periods equal rows. Now, I do ask questions to make sure you know the difference between a group and a period. Right? You need to understand what those refer to. Some of your ALEKS questions are going to ask you incessantly about what, it's in this period, it's in this group, what is it, right? And I'll give you a number for it. So the things that I want you to know, 1A is this guy over here. So these ones right here, these are your alkali metals. Your alkaline earth metals are right here. I want you to know the chalcogens, which is the oxygen guys, everything under oxygen, the halogens, and the noble gases. Now, in ALEKS, you may get asked about this group right here. I actually don't remember what the name of the group is. I had to look it up when I got asked that in ALEKS, but that's what we're typically talking about. Those are the ones I expect you to know. The reason I say that is because I often refer to, I'll say something to you like, I made something between an alkaline earth metal and a halogen. And so you need to know where we're talking about to be able to deal with that. Okay, so those are the ones I expect you to be able to know. You can, when you're studying, label this periodic table, but then you can't use that on the test. So you have to be able to think about that. Now, I'll tell you the trick that I used when I was a student. I would write all of that on my periodic table. I would sit and I would stare at it before I went to bed the night before I took the test. And then for like 10 minutes before I took the test. And as soon as I got into that test, I would vomit all of the stuff that I remembered onto the periodic table I was allowed to use on the test. So then I could use it. Okay. That is acceptable. As long as it doesn't start that way, it's okay. All right. And then we also talk about some general groupings. So we talk about almost everything on the table, and the majority of this, all of this stuff over here as metals. It's everything on the left of the table, except hydrogen. Hydrogen is not considered a metal, even though it appears in the alkali metals. Okay, it is not a metal. The non-metals are on the right side of the table, and we'll talk about why he's over here when we talk about the actual electron configurations. And then the metalloids exist along this little staircase. Now, you don't see this staircase on this table. You don't. And that's okay, because you need to know that they're in here. I'm not going to ask you which one's a metalloid. If I ask you about a non-metal, it'll be something that's up here that's obvious. If I ask you about a metal, it's pretty much anything else. I won't ask you about the metalloids. Okay? So those are things I need you to know about the periodic table, its structure, what information's on it, that kind of stuff. We talked about groups. Groups are the columns. The different groups have different names. Periods are the rows. The number of the row tells you the highest valence shell orbital that the element has. So we talk about the numbers of the rows. So row 1, row 2, row 3, row 4, row 5, row 6, row 7. And all of these fit in here, so it's 1 through 7. Those are the periods. So if it says period 2, we're talking about this row right here. Period 4, that's 1, 2, 3, 4, that's down here. Okay. Again, metals, most of the table, the metalloids around this stair step right here, and then my non-metals up here in the top right corner. Well, that was fun. One more time. Groups you need to know. And I'm going to pull up a slightly different view of this because I want to make sure that you're seeing what I'm seeing. So I'm going to pull this over here. I'm going to RSC. This is the periodic table I use all the time. I love this particular table. This is from the Royal Society of Chemistry, as you can see right here. And for me, it's really helpful because I can isolate things that I'm trying to show you guys. So if I want to focus on the alkaline metals, that's them. If I want to focus on the alkaline earth metals, that's them. If I want to focus on the chalcogens, that's them. And of course, I need to scroll over a little bit so you can see those. Look, those are my chalcogens. I want to focus on my halogens, that's these. And if I want to focus on my noble gases, that's these. Okay. If I want to focus on the metals, I can highlight everything that's a metal. Now notice that these guys have little blocks around them. That means they're metalloids. These are my non-metals. And you'll see the metalloids are also listed there. All right. If I wanted to focus on my period, that's period 1, there's period 2, and of course it includes the whole table. So those are my periods. The other thing that you can do in looking at this when we get to that part is we can highlight the S block that I talked about, that P block that I talked about over here, the D block that's in the middle, and the F block that's at the bottom. So these are ways that you can focus those things when we get to them and we're trying to talk about them that can help you to understand where they are. Seeing them on a table, a bunch of times, the colors will help you to identify where they are on a table that's not colored. Now, things that we talk about in terms of metals, non-metals, metalloids. Metals are good conductors of heat and electricity. Non-metals are poor conductors of heat and electricity. Metalloids have properties in between the two, and that's why if I select the metals, they're there, and I select the non-metals, they're there. It's both, okay? So that's our metalloids. These are the things that we call semiconductors. Those are also our metalloids. So that's stuff that we need to talk about. Cool with that. Now that is the structure of the table as we're going to talk about it for right now. We're going to start talking a little bit more about, atoms losing and gaining electrons, right? They do that. And one of the things that I was dying, I'm like, why? Why do they do this? Well, I know that they do it. They're called ions when they do that. And I know that they do. It's based on the type of material that it is, and where it is in the periodic table. What we find is that the majority of the metals become positively charged. The majority of the nonmetals become negatively charged. And these metalloids can do both. Okay, so my metals tend to be positive charges, and nonmetals are negative, and the metalloids can be both. And so that's, did I lose electrons to become positive, gain electrons to become negative, that kind of thing. And it's really based on where they are in the periodic table. Okay, we'll talk about that as time goes on. But for right now, I want to focus on how we can predict how many it will gain or lose based on its location in the table. Why? Because it's important. So we want to know what they're going to do, why they typically do what they do. We want to be able to predict some of these things. And when we're talking about, structure of the table, it's a good time to talk about. All right. Now, so now I'm going to come back. Here's my table again. Yahoo! I have this table one more time. We're looking at it over here, so I'm not going to leave that view up. This is the table that I'm talking about. I'm going to flip back and forth a little bit between these two so I can write one. How do I know what this is going to do based on where it is? Well, I said that the guys that were over here, the metals, they were going to become positive charges. These guys, they're over here, the non-metals are going to be negative, and these guys can do both, right? And positive or negative. The main group elements, when I say main group, that means these two columns right here, 1 and 2. And it also means this P block over here. So those 6. Those are my main block. Those I should be able to predict. All right. What I'm going to tell you is the way that you'll predict it is by thinking about how close they are to the nearest noble gas. So these are my noble gases, right? And the noble gases are the cool kids. They are what everybody wants to be. There are reasons that we want to be that. I'm not going to talk exactly yet about why we want to be that, but that's what I want to be. I want to have the same number of electrons as that noble gas does. So what I know is that as I go over and my atomic number gets bigger, right, I add more electrons, correct? Because I add more protons, so I add more electrons. So fluorine has one less electron than neon. And so if I add one electron to fluorine, I become like neon. And so neon doesn't want to lose any electrons. He tends not to be charged. So these guys tend to be neutral. Now, that's not always the case, but they tend to be neutral. These guys, being so close to noble gases, want to pick up electrons, for one, so they're always negative. And they only want to pick up one. So they're almost always -1, because they're one away from being a noble gas. Again, these guys over here typically want to gain electrons. These guys up here. Now, these metals do some other things. So I want to talk about the non-metals. Those are the ones that we're going to talk about predicting. I'm not going to ask you to predict any of the metals that are down here. These non-metals that are here, if they were to pick up 1, 2 electrons, they'd be just like that noble gas. And so we tend to see that these are -2s. And we don't often talk about the charges of other things. Nitrogen can and does occasionally pick up 3 electrons to be a -3. It's not common for these guys to do it. Nitrogen and phosphorus can and do, but it's not that often. Carbon doesn't really become charged because of where he is and his properties, so he doesn't normally become charged. We don't talk about boron becoming charged. He typically doesn't. But aluminum, these metals right in here, okay, they want to lose electrons. And if they lose electrons, then we got to talk about how we lose them. So now we're going to come and talk about the metals and how they lose, because they do. We said that. They tend to become positive charges. Now, if I look at Na, he's number 11. Now that means he has 11 protons and 11 electrons. The nearest noble gas to him is the one before him, which is this one over here, neon. So he's 10. So he's added an additional electron compared to the noble gas that's before him. So his best way to get to be that noble gas is to lose an electron. I have 11, I want 10. So if I lose 1, I become a +1. Oh. These guys have picked up 2 additional electrons comparative to the nearest noble gas. And so if magnesium loses 2, he has 10 electrons, just like neon does, and all of a sudden the world is happy. So that's +2. And occasionally when we talk about these metals over here, and it's usually only aluminum that we talk about it for, they can lose 3. And they become +3. Now, those are the things that I would expect you to be able to, okay, that's what happens. Those are the charges I would actually be able to expect you to guess. The +1, the +2, +3, the -1, the -2, and occasionally -3. Okay. Now, when it's a +3 and a -3, there are other ways for us to figure that out. So we'll talk about how we can do that later. But we can predict these charges just based on where they are in the table. And I wanted to mention that now before you started thinking that it was just mumbo jumbo that nobody knew. There is a reason that we can do it based on where they are. And we'll talk about that. It may be frustrating until we do, but that's how that works. Okay? Questions, comments, problems on any of that so far? Hope not, but if you do, please tell me, stop me, let me know. Okay? The next couple things we're going to talk about, these next few, are what we call periodic trends. Now, periodic trends can be very useful to us when we talk about things. And they're based on where things are in the table. So I thought this was a good time to talk about it since we're talking about things that you can learn from the table. They're also fairly simplistic. They're just ideas rather than things we calculate. So I thought I'd put it here, and then we'll talk about some of the other stuff the next time. The first thing I want to talk about is the effective nuclear charge, which has a lot to do with the atomic radius. Okay. Now I'm going to shift this view that we've got right here a little bit so that we're more even on sides. And one way to go. Okay, never mind. Okay. All right. So a little bit bigger periodic table. Move this over a little bit. You have copies of it, so hopefully that's not so bad. When we talk about effective nuclear charge, as I go across a row in the table from left to right, I'm adding both protons and electrons, right? So as I continue to add protons, I'm adding those protons in the middle. So remember we have this view where we've got our protons and our neutrons in the middle, and the electrons flying around the edge out here. And there may be a couple circles, and they're not really circles, but that's why we're talking about them, for the Bohr model. So all that stuff in the middle comparative to all the other stuff. So we've added these protons in the middle, and we've added other electrons, but they may not, they're flying all over the place. They really don't see each other that much. The positive center charge in the center gets bigger, but the negative charge isn't really felt. The addition of the other electrons isn't really felt on the exterior. And so because they're in the same space, that means that we're now looking at a more positive charge in the middle, roughly the same charge that we thought we had before. And so because of that more positive charge, things pull in. As we have more positive charges we go across, things pull in. And so what happens is that my atomic radius, as I go across my table, and I'm going to draw on the table that's back here. So my atomic radius as I go from here to here is going to get smaller. And again, that's because there's more positive charge. Now, as I go down, I get further from the nucleus. So if we're still talking about a smaller trend, we go smaller up. And this is, again, the atomic radius that we're talking about here. Okay, so when we talk about effective nuclear charge and atomic radius, they're both the same trend. My atomic radius gets smaller as I go from left to right and smaller as I go from bottom to top. The effective nuclear charge gets larger as I go from left to right and from the bottom to the top. The effective nuclear charge gets bigger as I go from top to bottom. Okay, so it's the opposite as the other. Okay, so effective nuclear charge, opposite trend is the atomic radius. So as the charge gets bigger, the radius comes in. Okay, so that's what we're looking at for that. Same trend for both of those things. Awesome possum. What we're talking about. And I'm going to label this for atomic radius. It's going to be smaller at the bottom, gets bigger going up, and it gets smaller at the top, bigger at the bottom. So smaller there and smaller as we come over. Okay, so smaller as I go across, smaller as I go up. Right? That's my atomic radius. And my effective nuclear charge is the opposite. And I'm just going to draw that so I can make sure that the effective nuclear charge gets larger this way. So same trend, but not smaller, larger. And this is the effective nuclear charge. Okay. So that's what we're talking about for that. I don't ask a lot of questions about the effective nuclear charge. I will ask about atomic radius. It's typically something that we deal with. So that's something for you to keep in mind. But they are connected. So just like I talked about, all right, we have these, they get big to small, big to small. So we're going smaller as we go from left to right, and smaller as we go from bottom to top. Okay. The radius gets bigger as I go down, right? That's what we would expect. I'm getting further from the nucleus, so I would expect it to take more space. All right. So that's my atomic radius. And that's again the trend that we were just talking about. We can talk about ionic radius, and I'll talk about this just a tiny bit. It doesn't look like a really good trend, and it really isn't. So it's not a great trend. However, there are some things that we can talk about. One is that if we're talking about a thing and it loses one electron and then loses another electron, so we're talking about these guys over here. If I lose one electron, then another electron, then I can pull in more because I've got more positive charge comparative to the negative. Okay, so a 2+ charge is going to be smaller than a +1 charge, which is exactly what we see. As I add additional electrons, every time I add them, then they're going to get bigger. So if I add 1, which is this I- right here, that's this kind of size. If I add 2, then we get a little bit bigger than that. Okay? So that's the kind of thing that we see there. I don't typically ask about that trend. There are some questions in ALEKS related to it, so that you get the idea of how that works. But because it's not a good, I can draw a big arrow on the periodic table, we tend not to talk about this so much. Right? You need to understand what happens when I add one or I take one away. What does that do to an individual one? That you need to know, and that's why we're talking about this. Okay. We also have to talk about something called ionization energy. Now, ionization energy is how much energy is required to be given to an atom to remove an electron. So how much energy do I put in to yank off an electron? Ionization energies increase as I continue to remove them. So the first ionization energy is always smaller than the second. So if I take off 2 electrons, IE1 is the ionization energy for the first thing. The first removal is always smaller than IE2, which is the energy associated with pulling off the second electron. Ionization energies increase as you continue to remove electrons, so that's what we're talking about. There is a very large increase in ionization energy if I remove a shell from an electron from an inner shell. That may not make a lot of sense right now. But what that means is that if we're talking about this prediction that we were talking about, right? We said that Mg, because he's right here, would probably lose 2 electrons, correct? And he loses 2 electrons, and then he doesn't do anything else. And that's because we've lost the 2 electrons that are here, and if I wanted to lose more, I'd have to lose them from the row inside of that. So the thing that's inside of it. And that's really a lot harder, okay? Once we get into what was the inside at one time, that makes it a lot harder. Now, generally speaking, my ionizations increase as I move from left to right in a period. So in my rows, so left to right, they increase because I don't want to take that electron off. When I'm a nonmetal, I want to gain electrons. So my ionization's energy will be very high if I'm over here where I actually want to gain electrons. So they increase as I come over here. These guys want to lose them. Those are very low energies. These guys don't, so they're very high energies. They increase as you move from left to right, and they decrease as you move down a column. So it's much easier to lose them down here because they're so far away, and it's much, much harder when you get up here because they're so close. Okay, so distance is a factor there for how easy it is in terms of the periods. Okay. So that's what we're talking about for those. So that's the trend that we would be talking about for ionization energy. We also have to be able to talk about electron affinity, and this is generally referred to as EA. makes a lot of sense, I think, is defined as the energy change that happens when an electron is added to an atom. So if I add an electron, it's how much energy changes. Now, if I add an electron to a metal that does not want it, so if I come over here and I say, hey, lithium, take another one, it's like, no, I don't fucking want that. So it takes a lot of energy to add it. Okay. The metals really don't want it. But for nonmetals, they really, really do. And so it's very, very easy for them to pick up an electron. That energy is negative because that's very favorable. So it's a negative energy. Positive energies are the ones that we are required when we add them. And so these metals have positive energies. So if these are negative and these are positive, then the trend that we have is that they get bigger going like this. Okay, because we're going from negative to positive. Okay, so that's what we're talking about. All right. Now, again, as we talked about before, it's generally harder to add electrons up here than it is down here. And the reason for that is because I don't have the space. Okay, so it increases as that favorability is better here than it is here. So the energy is much, much higher as I go that way. All right. We also need to talk about electronegativity. Now, electronegativity is different from electron affinity. It is defined as the pull an atom has for the electron within a bond. So if oxygen is bound to hydrogen, right? We want to talk about where the electrons that make up the bond live. Do they live by oxygen? Do they live by hydrogen? That's what we're talking about. I'll talk about this in way more detail later. It's defined as that pull. So we're talking about within a bond. It's not an individual atom. And as I go up and to the left, the electronegativity gets higher. So it's the same trend as the electron affinity. It wants those electrons more, so it's going to pull it in more. But it's not defined in the same way. So it's the same trend, but not defined the same. Okay? It's much more favorable to be over here as a fluorine wanting to pull those electrons toward me and not give them. Okay? So these are the trends. Woohoo! Lots of arrows. And this is one of the things that I used to regurgitate on my paper when I got, to my periodic table. My atomic radius, my trend for atomic radius. So smaller over here, larger over here. My electron affinity is, so it's negative down here, positive up here, so it's increasing there. Negative over here, positive over here, so increasing as we talk about that. My electronegativity, it doesn't want to pull it, it doesn't want it over here, it does want it over here, so increasing as we talk about that. Here, electronegativity, I don't really care versus I absolutely care, so increasing as we do that. Ionization energy, I really want to lose that electron versus I really don't. So favorable versus unfavorable, so it increases more energy is required to do it here. And again, it's all right if you take it versus I really don't want that to happen. I don't want you to take it. So again, higher energy required to pull that. Okay, so those are the trends that we're talking about for that. The other thing that we talk about in terms of trends is metallic character versus non-metallic character. Now remember I said that the metals are most of the left of the table. So as I go left, my metallic character increases. And as I go right and up, my non-metallic character goes up. So non-metals up here, all the metals down here. So that's why we're talking about that metallic character. Okay? Questions, comments, problems, concerns? All right. Now I'm going to break here. I will come back this weekend and do the walkthrough on the in-class practice. From here on out, you have answers for the in-class practice. I didn't do it for the dimensional analysis. stuff, but I did do it for the written ones for all of the lecture materials, 1 through 15. Now, I know a couple of them are missing it right at this moment. I need to get them put up. I couldn't find them on the computer that I'm at. So I need to make sure that those get loaded, but you should have answer keys for everything. You just don't have videos to walk you through those, and I will do my best to get them up as we go. Okay, so look for them to get posted on the weekends. All right, that takes us through our first week of lectures. I'm going to stop sharing here. I hope that you guys are still okay. Again, I'm going to try and have that chunked up a little bit when it gets posted so that you can say, okay, I need to take a break here. I need to take a break here. So it's not multiple videos anymore, but is chunked into chapters. That's what I'm hoping the new software will do for me. So if that works, great. If it doesn't, then we'll chat about that. All right, guys. Thank you very much. I'll talk to you soon.